So when we did the second moment of area calculations, we showed that we could have found Ix, Iy, and the product moment of area Ixy, right? After that, what we showed was that as long as I know those values of Ix, Iy, and Ixy, then I could apply some simple transformation rules to calculate the product, the moments of area, and the product moment of area about any arbitrary set of axes u and v inclined at some angle, theta to the x and theta to the y, right? And we developed to derive these three equations here um, quite simply. Now, since it's clear that IU varies with theta, there must be a possibility that there exists a maximum IU and a minimum IU. These are called the principal moments of area, or the maximum moment of area and the minimum moment of area, right? So what we want to do is we want to derive expressions for the maximum and minimum moments of area, or the principal moments of area. And we also want to look at what happens to IUV when IU is a maximum or a minimum, right? So to start this derivation, what we need to do is we need to look at what the expression for IU is, and since IU varies with theta, then to find where IU is a maximum for a particular theta, we want to basically uh, find the differential of IU with respect to theta. So firstly, what we're going to have is just simply the IU d theta. The first term is a constant, so it's 0. Second term, you're going to have 2 multiplied by 2 here. You're going to get rid of that half. You're going to get minus sine 2 theta, so it just becomes minus. Differentiate sine 2 theta here, you're going to get positive cos 2 theta, so you have to have that 2 out there. And you want this to be equal to 0. So this equation here is clearly going to be 0 if it is the case that, let's say, sine 2 theta divided by cos 2 theta, this expression is 0 if sine 2 theta divided by cos 2 theta is minus 2. And of course we know that sine 2 theta is really sine 2 theta divided by cos 2 theta is really tan 2 theta, right? Now the next step is that I can say, well, if I have right angle triangle, I have a right angle triangle, and this is 2 theta, then tan 2 theta can either be minus Ixy divided by or some simple trigonometry there, right? Uh, Minus Ixy divided by Ix minus Iy on 2 is going to give me tan 2 theta, or positive Ixy divided by minus Ix minus Iy divided by 2. It's going to give me tan 2 theta according to this expression we have here. Now, in both cases, you're going to have this expression, this hypotenuse r being equal to, must be equal to root of So in that way, it actually becomes relatively simple to define sine 2 theta. We can define sine 2 theta in two ways. We can say, well, it's either minus ixy divided by r, opposite over hypotenuse, or positive ixy divided by r. And in the same way we can say, well, cos 2 theta is either going to be positive ix minus iy divided by 2 divided by r, or negative, right? So very easily we've developed these sets of equations. Now remember, the goal is I want to find out where I1, or what is the value of the I, where I use a maximum or where it's a minimum. So I'm going to call this equation 1. This tan 2 theta is very important. I'm going to call this equation 2. And then I'm going to call sine 2 theta equation 3, cos 2 theta equation 4. If I substitute sine 2 theta and cos 2 theta, that is, I substitute equations 3 and 4 into equation 1, then I'll find out, get two values of IU. Well, the larger value is going to be I1, the maximum moment of area, and the smaller value I2 is going to be the minimum moment of area, right? And it makes sense because these are the values of theta for which the differential is equal to 0, right? According to equation 2, 3, and 4. So what I want to do is just substitute equations 3 and 4 into equation 1. And what I get is, I'm going to put I, and now I'm going to put 1 and 2 because I'm going to get two values. I'm going to put Ix plus Iy divided by 2. And remember, cos 2 theta can take plus or minus Ix minus Iy on 2r. So when I put a half Ix minus Iy in cos 2 theta, I'm going to put these two values. So in other words, what I'm going to do is I'm going to put plus and now I'm going to put plus or minus. You're going to see this is Ix minus Iy 2r. Yeah? And for the sine 2 theta term, which, well, firstly we need to put in Ixy, but for the sine 2 theta term, it's going to be minus or plus, based on the previous equation, Ixy on r. So we have two values here now, and we're going to kind of put 1, 2, simplify this a little bit. You'll recognize that you have plus multiplied by plus, positive, positive multiplied by negative, negative, so you could have positive, negative, and very easily you recognize that it's going to be similar way, negative by negative, positive, negative by positive, negative, simplify this a little bit again. When you factorize out 1 and r, this is what you get, right? Now it's interesting because if you look at what r squared is, r squared, Ix minus Iy on 2 squared plus Ixy squared, is actually this value here, r squared, right? Not r, because r is the root of that, but r squared is just going to give you this inside here, the argument inside the root, and it's actually exactly what you're seeing here. So actually it's r squared divided by r, so that's why sometimes we just write I1 2 is equal to r. And that's going to give you the values for the principal, maximum, and minimum moments of area. Now I'm going to write it over again. I'm going to say, well, this time I'm going to use some colors. I'll say I1 is going to be equal to Ix plus Iy divided by 2 plus the root of, and I'm writing like this just to show you that this is what R is. So this is what R is. This what is in this root here. Then I'm going to just write it I2 becomes minus right. So now you've been able to find you're able to find out what the values of the maximum I1 and the minimum I2 are in terms of Ix, Iy, and Ixy, right? Just by using these formulas here, which resembles very closely to our stress equations, of course, right? Where we find principal stresses. But the question is, well, at what angles do these principal stresses occur? Do these principal moments of area occur? And the answer is, it goes back to the equation 3 that we derived, sorry, equation 2, which is tan 2 theta p. And now I'm just putting p to stand for principal. I just had it as tan 2 theta before, but tan 2 theta p is going to be equal to, just write it in another color, minus 2I xy iy. It's going to be this expression here. So with respect to the trigonometry, when you find tan 2 theta p is equal to minus, and you substitute your values, and you get this term here, or this value here. When you find tan 2 theta p by finding the arctan, or the tan inverse of what goes on here, you're going to get two values, right? Now when you get two values, one of those values are going to correspond to I1, one of those values are going to correspond to I2. How do you know which one? Well, one of the simplest ways is just to take one of the values that you've gotten. If you take one, since you're getting two values from here, but if you take one value from here and you substitute it back into this IU equation, then if you get IU is equal to I1, then it means that angle corresponds to I1. If you substituted the second angle and you get I2, then that angle corresponds there. And I'm talking about angles, but obviously you're finding the tan inverse of 2 theta p. So it's going to be 2 theta p you find for, and then you'll need to divide it by 2 to actually get the actual angle. But those things we'll discuss in class through examples. This is just meant to be the derivation. Now the final thing I want to look at is just to look at, well, what happens to IU, what happens to IUV when we are at this principal angle to get I1 and I2, right? So if we've rotated it to the principal angle, such that we have I1, such that we have I2, what happens to IUV, right? And that becomes relatively simple, because all we need to do is we need to look at this expression here and for IUV, and substitute what sine 2 theta is and cos 2 theta, which we already derived. So let's quickly do that. So you're going to remember that. Take another snapshot. Yeah. So what we're going to do is we're going to substitute this, and you're going to see what happens, and it's a result you might be anticipating. It's going to be equal to a half and I'm going to just drop in sine 2 theta. It's minus plus IXY on R. Then I'm gonna so if you look at it carefully enough, you'll recognize it's minus IXY on R multiplied by IX minus IY on 2 plus IXY multiplied by IXY on 2R. So you're going to get 0 for the first solution. And if you look closely enough, you're going to recognize you're going to get 0 for the second solution if you have plus and negative here as well. So it means on the principal at the principal locations of your maximum and minimum moments of area, your product of area UV on those specific locations of theta p or theta principal is going to actually be 0, much like on the plane where you have principal stresses sigma 1 and sigma 2, your shear stress is 0. So that is basically it for the derivation, but as I mentioned, we'll discuss the applications in class.